All right, what is my physics teacher doing with drug paraphernalia, you may ask? This is a great example of what's called a hydraulic. Over here on your left side is a syringe with about a 1-inch diameter, and here is a syringe that has probably a fourth of the diameter. And so in between there is a fluid, water. It's just water with blue food coloring inside. And what you notice if you push the fluid back and forth is that it's kind of tough to push this side, but when it moves a little bit, you notice the right-hand side there moves quite a lot. And the reverse is true over here. It's quite easy to push this thing, and it does make this thing move, but it doesn't move very far. And so what you notice is very easy to push on the skinny side and tough to push on the fatter side. Well, so the deal here is when you're pushing, say you have a little battle against yourself. I'm trying to push this one down with this thumb and this one down with this thumb. What you find out is the skinny side will win. It's easier to push this one down. And it's because it's not a matter of having the forces balance with pushing the fluids. It's actually the fluid that's in between. It's actually a balance of the pressure. And so what happens is, since this has a larger area and pressure's force per area, you need a larger force in order to get the same pressure. So in other words, in order to tie, to be at like a stalemate between these two things, you actually have to push not as hard on this one in order to achieve equal pressure.
All right, so let's take a closer look at this. If we were to push on both sides with our thumbs as shown in the picture, and we want there to be like a stalemate, like the fluid doesn't go to one side or another, then really what needs to happen is the two pressures need to balance. Not the forces, but the pressures. Well, so since pressure is force per area, we can say that the force on the left divided by the area on the left equals the force on the right divided by the area on the right, right? Well, one thing to notice right away then is that since the area on the right is smaller, the force on the right can get away with being smaller in order for there to be a balance in the system. In fact, if we do a little bit of algebra and bring the area on the right over to the other side of the equation, you can see that the force on the left times a number that's going to be smaller than 1 equals the force on the right. Now, since in this system the diameters of the two tubes seem to be different by a factor of 2, which make the areas different by a factor of 4, in other words, the area on the right is only 1/4 of the area on the left, we can see then what that means is that whatever force we push with on the left, we can get away with pushing with only 1/4 of that on the right. In other words, a 10 Newton force on the right would actually defeat a 39 Newton force on the left. In order for it to be a tie, you'd have to have 40 on the left and 10 on the right. So the upshot is that by pushing with a small force on the right-hand side, on the small tube, that can make a large force on the left-hand side.
Okay. Well, so this thing is incredibly useful in a couple of different contexts. First of all, it may be the case that somewhere in a machine you need to push with a huge force, but maybe you yourself are not capable of applying the huge force. So what you do is you put yourself on this end where you just have to apply a small force, and you let the huge force be applied over on the other side. So the classic example of that is, for instance, for stopping something like a car or a mountain bike, you've got, say, the car going, and realize that you stop this massive car, but just by kind of flexing your cankle and pushing the brake pedal. Well, what you do is you put this part under your foot, the easy to push part, and this part goes near the rotor. And so then what happens is when you push on the easy part, you can apply tremendous force over here at on the fatter side, and it stops the rotor. Okay, so that's your classic hydraulic brake. Okay, now you might choose to use this thing in the reverse way, in that if you have a machine where you have like a tiny motion in one place and you need to create a large motion from that tiny wiggle, what you can do is have the tiny wiggle happen here, the tiny movement happening there, creating a very large movement over on this side. The cost to you, though, is in order to push this side, you need to push with quite a large force. Okay, so final comment about this thing. Notice that this is a device kind of for for cheating force, you can, by pushing with a small force here, you can create a big force on this side. So people have figured out ways to cheat force. What we can't do is treat the product of force and distance, because that is work or energy. And so realize that over on this side, you're pushing with a small force over a long distance. Over here, that creates a large force over a short distance. So this product of force and distance is basically the same on the two sides. And that's a statement of what's called conservation of energy. And we have not figured out how to cheat that, but we are clever enough to cheat the amount of force that we have to apply to make something happen.